Hi and welcome to this video on estimation, approximation and rounding, maths made easy. Now this is used to get a rough answer. The answer we get is not exact and we do it to get the answer quickly. For example, if we've just done a complicated exam question, right at the end we want to double check it, we'd used rounding or approximation or estimation just to double check that the answer we've done is right. Or when we're out shopping and we want to get an estimate, a rough estimate of the value of the shopping we've done, we'd use approximation and then tot it all up and make sure that we've been charged the right amount. So the rule in rounding is that if we've got numbers less than 5, it gets rounded down. Numbers that are 5 or higher get rounded up. So let's just go through that rule. So if we've got this decimal 2.47 and we want to round it to one decimal place, so here we've got the decimal point. This is the place after it, which is at number 1. So this is one decimal place after the decimal point, and we want to keep this number as 2 point something. So we look at the next number after the first decimal point, and that's 7. So remember this rule, 5 or higher gets rounded up, so we increase this number by 1, so this becomes 2.5. So 2.47 rounds up to 2.5. So we've got 3.42, we want to round that to one decimal place. Look at this 2, so look at the rule, numbers less than 5 get rounded down, so rounded down this remains, the 4 remains as 4, so that's 3.4. Longer number, again the rule's the same, so if we've got 1.473452, we look at the first decimal place, which is 4, and then the number next to it. So this number 7, is it 5 or higher? Yes it is, so it gets rounded up, so it becomes 1.5. We want to express 0.36374 to 3 decimal places, so like here we did to 1 decimal place. We count after the decimal point 3 places, 1, 2, 3. So the number we want is going to be 3 decimal places after the decimal point. Look at the next number. So is this 5 or higher? Yes it is. So this 3 then changes to a 4 and our answer is 0.364. So in estimation we try to get a good guess, again, which is not exact. And there's no single method of doing this. So for example, if a shop's selling an item at 195 or 199, they often do this because it seems less than £2, and when people see £2 they get a little bit scared. Oh, that's a bit expensive. But when they see 1 and then something, they look at it and say that's about £1. But it isn't really, because when we're estimating, say we're buying 4 pairs of socks and they cost 195, when we're estimating, then this 195, we'd say that was roughly £2. So we bought 4 pairs of socks, so that's £2 times 4 is £8, and the shop charges £9.75, so that's not right. It should be around £8. So we're an overcharge. Let's go to customer service and sort this out. Here we've got to add 2146 and 4876. So this is 2146. So to the nearest thousand, that's 2000. This is 4876. So to the nearest thousand, that's 5000. 5000 plus 2000, we estimate to be 7000. When we did this calculation, we rounded the numbers up or down before we did the addition, before we did the calculation. So let's try it with multiplication. So 204, that's roughly 200. 494, that's roughly 500. Multiply 200 by 500, we get 100,000. So estimate of these two numbers multiplied together, 100,000. While we're on the subject, let's just see how we multiply 200 by 500 quickly. So first of all, multiply the 2 by the 5, we get 10, and then there's 1, 2, 3, 4 zeros after the 10. So 10 and 4 zeros, 100,000. multiplying decimals and estimate by rounding. So we've got this decimal and then this one. This is roughly 0.2. This is roughly about 30. So 30 times 0.2 is 6. How did we do that quickly? 30 times 0.2. Well, 30 times 2 is 60. And this 0.2 is the decimal we're interested in. So move it. When we're at 60, the decimal point is here by the 0. Move it left one place. And when we do that, we get the 6. So 30 times 0.2, 6. Also, we've got little bits left over. So we've got this 4.5 left over, which is roughly about 5. So 5 times 0.2 is 1. So 6, we can add another 1 to that. So that gives us a better estimate, which is 7. So 6 plus 1, 7. Remember, even the 7 is not an exact answer, it's an estimate. Sometimes we're asked to give the answer in terms of so many significant figures, say 2 significant figures or 3 significant figures. So earlier we did decimal places, so here we're going to go over significant figures. The way we do this is the same as rounding to a decimal place, but instead of starting at the decimal point, we start at the beginning of the number. So here we're going to round this 12.756 to 3 significant figures. So we start here, so 1, 2, 3 from the beginning of the number. So the answer is going to be 12 point something, not nothing else after that. So this will be up to 3 significant figures. Look at the next number. Is that 5 or greater? Yes, it is. So we round up, and this will give us 12.8. 135.45 to 2 significant figures. So this here is the first significant figure after the number. This is the second. So we want to look at the next number, which is 5. Is that rounding 5 or greater? We've got to change this 3 to a 4. So this gives us 140. Don't forget the 0. Here we've got 2 significant figures, but the 0 has to be included in the answer. It's important to keep the place values the same by using 0 and keep the decimal point in the same place. So the decimal point would be here. Okay, after 135. If we just give the answer as 14, that would be totally wrong. So that's an important fact to remember. If we're adding a lot of numbers that are similar numbers, then we can get we can look at the numbers and get a rough average. So here we've got 225, 220, 282, 212, and then these larger numbers again, 265, 270. So roughly that's about average 250. So 250 multiplied by the how many numbers there? 1, 2, 3, 4, 5, 6, 7. 250 times 7, 1,750. So the sum of these numbers, an estimation, 1,750. We're going to look at upper and lower bounds. So if a length is given as 3.4 meters to the nearest 0.1 meter, then the real value could be between 3.4 plus or minus 0.05 meters. So the nearest 0.1 meter we divide by 2, so that gives us 0.05, and then the upper bound would be 3.4 plus 0.05, and the lower bound would be 3.4 minus 0.05. So it gives answer of 3.45 meters and 3.35 meters as the upper and lower bounds. So let's do a question with that, using the upper and lower bounds and maximum and minimum possible values. So here we've got like a floor area that we measured, 3.6 meter wide, 4.2 meter long. So the upper bound, or the maximum possible value, and it's measured to the nearest 10 centimeters. So again, it's going to be plus or minus 0.05 meters. So the upper and lower bounds of the 3.6 is going to be 3.65 meters and the lower bound 3.55. So that's 3.6 here plus 0.05 and 3.6 minus 0.05 gives us these two values. And then again for this 4.2 meters, the upper bound 4.2 plus 0.05, which gives us 4.25, and 4.2 minus the 0.05, 4.15. So we've got the upper and lower bounds, and then the maximum area is given by these two maximum values multiplied together, and then the minimum area is given by these two minimum values multiplied together. The percentage error, we don't use these two values, we use the maximum and minimum values. So the percentage error is the difference between these two values, the maximum area and the minimum area. Okay, so don't use the area 3.6 by 4.2, we have to use the maximum area and the minimum area, so it's the difference divided by the maximum area multiplied by 100, and that gives us the percentage error.